Good morning, everyone. I hope you're all well. It's Dr. Bennett here again, and today we're going to be talking about moments of inertia. So we're starting chapter 8 of the textbook. So before we get into it, I thought what we'd do is just revise what we mean by these two terms, moments and inertia. So inertia, you should all know, is basically the resistance of an object to change its velocity, and that could be in either magnitude or direction, right? And a moment, as we've seen throughout this course so far, is how we measure the tendency of a force to cause a rotation. So a moment of inertia then, and by the way, I'm going to start using this abbreviation MOI, and that's given the symbol capital I. So this determines the extent to which an object resists rotational acceleration about a given axis. And we calculate the moment of inertia by multiplying the mass of an object with the distance of that mass from the axis of rotation. And if we have more than one object or more than one particle that's rotating, we sum all of the individual pieces up. So a very easy example to think of when looking at moments of inertia is this swing ball, or as you guys would call it, tether ball example, where you have a ball rotating around some pole, and if we consider each of these balls as just a point mass rotating about this central axis, we can look at the effect that changing the mass and the radius of the rotation has on the total moment of inertia. So in this first example up here, we just have a mass m rotating at a distance r from the axis of rotation, and that gives us a moment of inertia of just mr squared. So what happens when we double the mass? Well, if we double the mass at the same radius of rotation, we get double the moment of inertia, right? So 2mr squared as opposed to just mr squared. But what happens if we have the same mass but at twice the distance? Well, we actually get 4 times the moment of inertia. We get 4mr squared, right? Because the radius is squared. So actually the distance from the central axis to the point mass is actually the driving force in increasing the moment of inertia rather than the mass. So that's something to think about, and a real life example. And the other thing that moments of inertia are related to is this notion of angular momentum and angular velocity. And those three things are related by this formula here. The moment of inertia is the angular momentum over the angular velocity. So in real terms, what this actually means that if we increase the moment of inertia but want to keep the same angular momentum, then the angular velocity must decrease. So think about an ice skater. That's the typical example of this that's given in textbooks. So when an ice skater is spinning on the spot, right, and they have their arms out and then gradually bring their arms in closer to their center of rotation, their angular velocity, their spin rate increases, right, because they've brought more of the mass of their body towards the center of rotation. So that's why that works. Alright, so let's go ahead and formalize and generalize what we've just been talking about for an arbitrary shape in the two-dimensional space. So first let's consider the moment of inertia about a line or an axis. So here we have the xy plane, we have this arbitrary blob with area capital A, and we can split this total area up into these little pieces dA, as we've seen before, and then we can calculate the moment of inertia of the whole area A about the y-axis by summing up the individual areas dA multiplied by the distance or the radius of rotation from the y-axis, right? And we sum all of those little pieces up to find the total moment of inertia about the y-axis. So here we're assuming that area is proportional to the mass of A. If we assume that this shape has a uniform density, right? So that's why we can do that. So if we write this equation in integral form, we just take the integral over the whole area of the distances from the x-axis of all the individual pieces with respect to A. And when we calculate this, we'll end up with a solution in this form, right? The moment of inertia about the y-axis is some coefficient squared, which is denoted with this kappa sub y to denote that it's about the y-axis, multiplied by an area. And this kappa is called the radius of gyration. So let's have a quick look at the this solution form. Well, the units for moments of inertia, if we do some dimensional analysis on these two components here, area obviously has units L squared, and a radius is going to have units L, right, because it's another distance. So the radius squared will have units L squared also, and therefore the units of moment of inertia is just going to be L squared multiplied by L squared, so we're going to have units of L to the 4. So that's just a quick way of checking that you've got the right, that your solution is in the right form, right, if the units are consistent. And similarly, as we've seen before, if we choose to find the moment of inertia about the x-axis, then we're just dealing with the radius in the y direction. So the moment of inertia about the x-axis is the same integral form, but just now we have y squareds appearing instead of x squareds. So that is moments of inertia about a line. We can also find moments of inertia about a point. So if we draw our same arbitrary blob in the xy plane, which has total area A, again split this up into little pieces of area dA, then we can also calculate the moment of inertia about a point. So in this case we're going to look at the moment of inertia about the origin. So that's going to have a radius r, which we can calculate if we know the distance in the x-axis, the distance in the y-axis with a little bit of trigonometry, right? And then we can calculate what's called the polar moment of inertia. So that just means about a point, right? In this case about the origin, and we denote this with a capital J instead of a capital I to make the distinction between the moment of inertia about a line or an axis and the moment of inertia about a point. And we give it a subscript O or 0 to denote that it's about the origin. So what we do is we take the integral over the whole area of all of these radii from the origin to all of the little pieces dA, and integrate r squared with respect to a. And as we've just shown, this r squared can be written as just the sum of x squared plus y squared via this little bit of trigonometry down here. And then using the laws of integration, we can split this integral up into two separate integrals, the integral over a of x squared with respect to dA with respect to a, and also the integral over a of y squared with respect to a. And look what we have. Well, we have two separate pieces that are the same as what we had before, right? The integral, the moment of inertia about the y-axis and the moment of inertia about the x-axis. So to find the moment of inertia about the origin, we just find the moment of inertia about the x-axis and the moment of the inertia about the y-axis and add them together. So now let's go ahead and have a look at a couple of examples. So for the first example then, let's go ahead and have a look at this generic triangle of base B and height h, and go ahead and calculate the moments of inertia about the y and x axes. So first of all, let's deal with the moment of inertia about the y-axis, and as such we have to split our triangle into little strips of width dx, and just using basic equation of a straight line, we can work out the height of these strips. So this straight line is given by y equals the gradient, which is the difference in y over the difference in x, so h over b multiplied by x. The intercept is at the origin. So if we know the height of the strip at each point dx, right, then we can work out the area of these little pieces dA, right, just as the width dx multiplied by the height h over b times x. So then once we have that piece of information, we can go ahead and put it straight into the formula we've just discussed. The moment of inertia about the y-axis is the integral over the total area of x squared multiplied by the integrated with respect to a. So if we're dealing with distances from the y-axis, then we're dealing with an integral between 0 and b, right, of all of the x squareds multiplied by dA, which we just worked out here, h over b times x with respect to dx. So so what I've done here is I've just taken h over b, which is a constant, out of the integral, tidied it up a little bit, and then integrated x cubed with respect to dx to get x to the 4 over 4, and then plugging in the values 0 to b into there, I should get a quarter hb cubed. Okay, so that deals with the moment of inertia about the y-axis. So what about the x-axis? Well, in this case we basically do the same thing but the opposite way around, right? We're now looking at the moment of inertia about the x-axis, so we split our triangle into little pieces or little strips of depth dy, right? And then we need to find these little areas dA, right? So if we know the equation of this straight line is y equals h over b times x, then we can just rearrange that for x, right? So that's what I've done here. I've just rearranged the equation of the straight line for x so that I can work out the width of these strips of depth dy. But if x equals b over h times y, so for any given x, I'm working out this distance, right? The wrong side of the line. So in order to get this length, or this width, I need to take b and subtract this piece, right? So hopefully you can all see what's happening there. If I take any x along the x-axis here and plug it into this equation to find the width of this given strip, I'm going to be finding this distance here between the y-axis and my point x that I'm choosing. So to get this side, I need to take b and subtract that, right, to get this. So the width of a strip dy at any given x position is b, which is the total length of the triangle, subtract this piece, which is this piece in here. So therefore I can work out these little areas dA just as the height, which is dy, multiplied by the width, which we've just worked out. And then once I know that, I can go ahead and plug that straight into the equation for the moment of inertia about the x-axis, which is the same as it is about the y-axis, apart from we now have y's instead of x's, and we have everything now in terms of y. So again, plug that in. Now I'm dealing with an integral between 0 and h, right, instead of 0 and b. So I go ahead, calculate that integral, and I should get 1/12 bh cubed. Now for a standard shape like a triangle, we can use the appendix in the back of the textbook to check our answers, right? So let's find the results for a triangle. Here we go, look, page 578, and we can see that the moment of inertia about the x-axis is 1/12 bh cubed, where our dimensions are given like we just used in the example question: base b, height h, same orientation of the triangle. So we should find the moment of inertia about the x-axis as 1/12 bh cubed, which is exactly what we got here. And the moment of inertia about the y-axis is 1/4 bh cubed, which is what we got here. So we can always check for standard shapes such as a triangle or circles, semicircles, squares, rectangles, that kind of thing, by referring back to the appendix and the properties of areas and lines for standard shapes. So now let's go ahead and have a look at a slightly more complicated example. So finally for today then, we're just going to take a look at this example here, where we're going to calculate the moment of inertia about the x and y axis of this area below this curve, y equals 2 minus x squared. So we're looking at the area bounded between the positive x and y axes and this curve between x equals 0 and x equals 1. So as we saw for the previous example, to find the moment of inertia about the y-axis, we split this area up into vertical strips. We find the height of those vertical strips based on the definition of the line which bounds the area. In this case it's 2 minus x squared. So therefore the area of each of those little strips is just the height multiplied by the width of the strips, which is dx. And then we plug that into our formulae for finding the moment of inertia about the y-axis as this integral equation For the moment of inertia about the y-axis, we're dealing with distances along the x-axis, so we're integrating between 0 and 1 of x squared multiplied by dA, which we calculated here. So if we work through that, calculate that integral, we get almost 0.5. So please check that you can get these answers, as with all of the previous ones as well. Make sure that you can work through these yourself too, and have a look at the recommended problems as well. So to calculate the moment of inertia about the x-axis, we need to, as we saw in the previous example, split this area into horizontal strips this time of height dy, and therefore we need the width of the strips. So we rearrange the equation of the line for x so that we now have everything in terms of y for our integration. I've found the y coordinates here, so I know what I'm integrating between. And then I can work out the area of those little individual horizontal strips as the width multiplied by the height. So I haven't drawn these out like I did for the previous example, but if that helps you to do this kind of thing, right, then please go ahead and replicate that for this problem. But there's one thing that we need to remember here for this problem, and that is that when we calculate the moment of inertia about the x-axis in the way that I've just formulated it, and looking at splitting this area into horizontal strips bounded by this curve, is that I'm only calculating essentially this bit here, right? Because that's the part that's bounded by the curve between y equals 1 and y equals 2. So I have this extra piece here, this 1 by 1 square, which I need to add in to the moment of inertia calculation as well. So that's why I have two terms in here for calculating the moment of inertia about the x-axis. I have this part, which is all of my pieces that are in terms of y that I've just calculated here, which corresponds to this piece up here, plus the moment of inertia due to this 1 by 1 square. So I can calculate this integral, this first piece, in the same way as I have up here and in the previous examples, and then I can look up this moment of inertia due to a 1 by 1 square as a standard result in the appendices. So if I go into my appendices, Appendix B, properties of areas and lines, I look for a rectangle or a square, right? So here we go. If we have a 1 by 1 square, B will equal 1 and H will also equal 1, so we find the moment of inertia about the x-axis as a third 1 times 1 cubed, which is just a third, right? So I'll come back over here, I've got this extra third to add on to this integral here, and I get 1.69 as the total answer. So again, just to explain what's going on here, just to repeat what I've just summarized what I've just said, is that technique where I split this into horizontal pieces and then calculate the little areas and add them all together is just going to relate to this upper piece here, because that's the part that's bounded between y equals 1 and 2, right, by this curve. So then I have this extra piece of the 1 by 1 square to add on to form this total area, and therefore the total moment of inertia. So that's it for today. I hope you're all staying well, and look forward to speaking to you all again soon.